Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, for my calculus students, especially my AP calculus students, we have some problems concerning the intermediate value theorem, also known as IVT. We're going to recap what IVT tells us about and how to carefully write statements using the IVT. There really aren't a whole lot of different applications. There are a couple of other circumstances, but this will cover our purposes. Give yourself about a minute and a half per question, so let's say a total of like 9 minutes, anywhere between 8 and 10 minutes. Seems reasonable. Give this a shot for yourself first, and then when you're ready, you can unpause the video, come on back, check out how we did it here. Okay, so a quick recap of the IVT. IVT is one of the handful of theorems that you're going to learn and need to use, or at least you're going to need to direct your attention towards it and bring it up a couple times in your calculus careers. And there are requirements to any of these theorems. If a function does not satisfy the requirements, then we cannot use the theorem's conclusion. So the IVT requires continuity. The function you're talking about needs to be continuous on whatever interval we're interested in, so it would be something like a to b. As long as we have continuity, we can use the intermediate value theorem. Now let's break down what this theorem says, just using the first word there, intermediate, or I guess first two words, intermediate value. Let's suppose that on an interval from a to b, the function value starts off at f of a, which I'll put down here, and f of b, which I'll put somewhere higher. If the function's continuous, that means there has to be an unbroken path from f of a to f of b, and it still has to follow the rules of a function, so it can't fail the vertical line test. Otherwise, it's no longer a function, so you can't do whatever you want. You could certainly go outside of this box, come back down. But in any case that is valid, you for sure will reach all of the values in between all of these intermediate values. It's kind of like saying, in order to go from, say, the 3rd floor to the 7th floor, you need to pass through all of the floors in between, the intermediate values. And of course, f of b could be greater than f of a, or f of a could be greater than f of b. Either way, we're going to have this sort of range of values from f of a to f of b, all of the intermediate values, that we can say confidently the function will reach that at some point. Now I want to emphasize that this theorem is merely an existence theorem. It doesn't find us where the function hits that value. It just tells us that it does hit it somewhere on the interval. Okay, so let's look at some examples. If it isn't already clear, and you haven't already given an attempt, and my spiel at the beginning of this video wasn't good enough, just keep watching it again, I guess. But other than that, you'd be ready to get started here. So we're going to verify that the intermediate value theorem guarantees that there is a zero. In order to verify that, we need to for sure guarantee that f of 1 and f of 2 are above and below 0. Doesn't matter which one is above and which one is below. Just as long as 0, I could say it better actually. We need to guarantee that we want 0 must be an intermediate value. What does it mean to be intermediate? It just means in between. It's just a fancy math way of saying in between. So 0 must be an intermediate. If we plug in 1, we get f of 1. And that's going to give us, oh, why did they give us these kind of weird numbers? Let's see, 2 and 1/16, so 33/16. But if I plug in f of 2, or rather if I plug in 2, let's move on the other side so I have space. I'm going to get, oh, that's why they have the 16 there. 2 to the 4th is 16. 1/16 of 16 is 1. Minus 2 cubed, which is 8, plus 3. So we have 1 minus 8 plus 3. Or in other words, 4 minus 8, which is a negative 4. So, yes. And the reason why is specifically because f of 2 less than 0, which is less than f of 1. So therefore, somewhere in between, we will be crossing the 0. We don't know where we'll be crossing the 0. We don't know if it's closer to the 1 or closer to the 2, but somewhere we will be crossing 0. All right, let's look at the second problem. We're going to do the same thing. We're going to verify the endpoints and make sure that these are on either side of 0. They have to be on opposite sides of 0 to guarantee that 0 is intermediate. That kind of just makes sense. To make sure 0 is in between them, we have to make sure they are outside of 0, but like on opposite sides. Okay, go ahead and plug in negative 2, and you'll get a very negative number. And if you plug in positive 1, you'll get 2. So again, because 0 is in between these two y values, it's not just because 0 is in between negative 2 and 1. I want that to be clear. This is because f of negative 2, which is the y value, is less than 0, which is less than f of 1, which is the y value. Okay, good. And now they give us a trig function. So notice they can give you any function and any interval, but if they want you to do it without a calculator, they're not going to give you, something really difficult to plug in. Let's plug in 0, see what we get. You don't just get 0 on everything. You get 0 minus 0 minus 1, so that's a negative 1. And then when we plug in pi, we get pi squared minus pi minus cosine of pi, which is negative 1. So pi squared minus pi, I think it's obvious that that's greater than 0. Since pi is like about 3, pi squared is like 9, so pi squared minus pi is close to 6. I don't know what it is exactly, but it's pretty close to 6. And then if we add 1, that's definitely greater than 0. So these two endpoint values have an intermediate of 0. Doesn't mean that 0 is directly in between, but it's somewhere in the middle. Okay, great. Now let's look at some slightly tougher problems. Still not too bad. I want you to verify that the intermediate value theorem applies to the indicated interval. So we need to make sure, again, that 11 in this case is an intermediate. How do we do that? Well, we have to check the endpoints. So we plug in 0, see what we get. That's pretty easy. We just get 1. Plug in 5, and that's going to be something bigger than 0 for sure. Let's see what it is exactly. 5 squared is 25, plus 5 is 30. So 30 minus 1. Now we can say, since we know that f of x is continuous, and 0 is in between f of 0 and f of 5, by the IVT, f of x equals, whoops, why did I say 0? Since 11, pardon me, is between f of 0 and f of 5, so between negative 1 and 29, by the IVT, f of x equals 11. I could say, for some x on the interval from 0 to 5, right? If If I go from -1 to 29, I had to have crossed through 11 at some point. Okay, let's check this one next. We're going to plug in the endpoints. So you can see that it comes down to basically plugging in the endpoints as long as we know that the function is continuous. If it does not meet the conditions, then we have no business even trying to piece together the intermediate value theorem. We don't want to use the conclusion of the theorem if the conditions are not met. So we have to make sure that it's continuous. These are pretty nice functions. They're polynomials and such, so they are continuous. Does it want me to find the value of c? Yeah, thanks. Thanks for the reminder. So we want to set this equal to the function, which means we're basically going to do x squared plus x minus 1 equals 11. Therefore, x squared plus x minus 12 equals 0. And this is some pretty easy algebra. We just factor this up. So this is true when x is -4 or when x is 3, but we're only interested on the interval from 0 to 5. So this is still a true statement. This is correctly using the IVT. Then if we were curious to find out where it actually happens, we have to set up this equation. But I want to be clear that this remainder of finding the value is not part of the IVT. The IVT is just an existence theorem that says at some point we'll get it, and then we did some algebra to actually find it. X equals 3. Okay, let's take a look here. F of 0 equals 8. Of course, that's a really easy one to plug in. F of 3 is going to give us -1. So for sure, f of c has to equal 5 at some point for some x on the interval from 0 to 3. Now let's find out when that actually happens. So x squared minus 6x plus 8 equals 5, which means x squared minus 6x plus 3 equals 0. And we're going to have some radical solutions here. This is not going to factor nicely. Go ahead and use the quadratic formula carefully. -b, but b is already negative, plus or minus the square root of b squared minus 4 times 1 times 3 over 2. And we need to check when we get this simplified a little more whether or not both of those solutions are valid in the interval. So here we have 6 plus or minus square root of 24, which you can simplify. All of these pre-calculus skills are a given at this point. You need to be very smooth with them. So we get 3 plus or minus root 6. Well, root 6 is bigger than root 4, which is equals to 2. So root 6 is bigger than 2. So 3 plus root 6 is bigger than 3 plus 2, which is 5. That means it's outside of the interval. We're not going to use this one. We're going to use 3 minus root 6, which is a little bit less than 1. Don't know exactly what it is. It's a little less than 1. And so it is on the interval from 0 to 3. All right, last one here. Interesting deal. They give us a cubic function. This one might be a little bit tougher to solve. Let's find the values at the endpoints. We're going to have -2, of course, if you plug in a 0. It's pretty easy. But then if you plug in a 3, you're going to get 3 cubed minus 3 squared. So let's write that out. 27 minus 9 plus 3 minus 2. So 18 plus 1. That's 19. Great. And since 4 is in between these values, we can guarantee that it is going to cross through at some point. Notice that that was the tactic. Every time we need to make sure that the value for the function is actually intermediate, that it's actually inside of those boundaries. Okay, therefore we know f of c equals 4 at some point. Let's find out where it does. Minus 2 equals 4, which would mean that x cubed minus x squared plus x minus 6 equals 0. Now this one you would have to find your solutions by using the rational root theorem. So you kind of have to guess and check unless you were using Desmos. A good guess to check is always 1 and -1 just because they're so easy to plug in. That's not going to happen to work for these, but those are some good guesses to plug in. Also notice that our interval is from 0 to 3. So we shouldn't have to plug in any massive numbers here. Let's try to plug in 1. We get 1 minus 1 plus 1 minus 6. That's just going to be -5. That's not 0. Let's try to plug in 2. We're going to get 8 minus 4 plus 2 minus 6. That's 10 minus 10. That one is going to give us 0. So it looks like x equals 2 is a solution. Even though I didn't solve this down formally, I didn't break it down how we would normally break down polynomials, what you learned in pre-calculus. This is just a quicker method for guessing some solutions here. And we did have more information about it, that it has to be between 0 and 3. So we had very few options we had to exhaust. It wasn't that difficult to go through those options. All right, this is a glimpse of how we use the IVT. I will have a follow-up video for this weekend that covers using the IVT with tables and a graph given. But for now, that's enough blab out of me. I'll see you guys next time.